Hi, everyone. Continuing with our topic on environmental stressors, topic 15.2 is about air quality and adequate ventilation. Air quality, not just in terms of pleasantness, but in terms of the temperature that may be required for pleasantness, as well as oxygenation. That's a major factor in healthy human metabolism to perform work, right? So yes, there are a number of workplaces where ventilation is a critical need and is a challenge. So anything that is, subterranean, underwater, ships, submarines, mines, high altitude conditions, where the oxygen is thinner. Also polluted environments can be problematic for oxygenation. When there is not enough oxygen, it's a particularly dangerous situation because the human will not necessarily be aware that the oxygen levels are low. So that we don't really have an internal sense for the oxygen content. We just have an internal sense for the carbon dioxide buildup. So, if we hold our breath, the need for us to respire, that desire, that gut feeling like I gotta breathe, that comes from a buildup of carbon dioxide, not from an absence of oxygen. So there you go. So oxygen, the absence of oxygen isn't something that is always very apparent. Now, there are signs of low oxygen in your environment, usually things like your vision starts to be a little bit constrained. You may feel lightheaded. You feel, potentially kind of dumb, for a moment. And so, yes, it negatively affects perception, motor, cognition. You can be, like really stupid on low levels of oxygen and not realize what's going on. We call this hypoxia. That's too low oxygen, or anoxia, I guess would be the absence of oxygen. There are also other, besides oxygen, there are other harmful gases that we don't have a natural sense for. So carbon monoxide, for example, colorless, odorless, we don't have senses that can pick up on it. That's why we have other machines, devices to do carbon monoxide detection, because we know it is a dangerous gas, right? So like, coming from the exhaust of gas-powered engines. All right. This is an example, a tragic one, but one, I bring these up once in a while. This was a case where there was a private jet, but it had a pretty decent passenger list on it, flying from Orlando and attempting to go to Dallas. And what happened was there was a loss of cabin pressure. I guess this is the investigation after the fact. And apparently, after, foreshadowing, there was a crash of complete loss of life and craft. But what happened is, I guess shortly after takeoff at some point, there was a loss of cabin pressure. And so, it's not maybe something that would be noticed if it was a small leak. I don't know how this happened, I guess. But in any case, we had people in, the cockpit as well as the cabin that were becoming hypoxic and maybe didn't quite realize it, or otherwise couldn't get the oxygen they needed. Everybody on the aircraft was incapacitated, but it was in autopilot mode. So they had climbed up to an altitude, where the oxygen levels are low, but also where you would say, okay, now, hit cruise and let's take the easy part of the flight. So rather than, instead of making their prescribed turn here to head towards Dallas, this uncontrolled aircraft just kept going straight. And so there are, this isn't like somebody with a camera, this is a digital rendering, but they did have, fighter jets do flybys and look inside, and it looked like everybody passed out. So, this is a clear case of, by the investigation, the effects of, and potentially the, catastrophic effects of not having adequate control of oxygenation in the workplace. Okay. And so there are domains where the oxygen is just going to be hard to get at times, and a lot of them are up. So yes, high, flight, being in the high atmosphere has low oxygen. Obviously, space operations, the absence of atmosphere means the absence of natural oxygen, so you have to have control in your space. But there are also, in those domains, ways to train to, number one, recognize the signs of hypoxia, because again, it's not like your body naturally tells you that. You kind of got to be paying attention, and also ways to basically train your body to function, at least functionally, in low levels of oxygen. So they call this hypoxia training. And I have never seen these with my own eyes, but I work with a number of groups that use these. They tend to be, like part of military sorts of settings, so they're a little more controlled. But yeah, the ability to control oxygen intake, and to the detriment of the pilot, this is a major part of a lot of flight training, at least in military cases. All right. Okay, so those are very interesting domains and everything. The vast majority of us are not looking to become, engineers, and also fighter pilots. Some of us are, but most of us will be thinking about, an office setting, a workplace where a lot of humans are coming together, and are we getting enough oxygen into this environment in order to, number one, keep our workers oxygenated. And number two, we also have to ventilate a lot of other equipment that, both for heat reasons and otherwise, needs moving air over it. And it's a lot of our computing equipment are very big time, heat producers. So there are equations we can work with here, and most of this is handled automatically by those big devices we call air handling units. I've got a picture here in a minute, but right now on the graphic, it's this guy. And there's quite a bit that's handled already there, but engineers are the ones that design and manage and maintain these devices. So it's interesting to know how they work, these air handling units. So we know we need a certain amount of outdoor air. That's the ultimate source of oxygen, right? Outside. When you are if you're in an enclosed space with oxygen consumers in there, that oxygen level depletes. So you need to refresh it with more outdoor air, right? The issue here is sometimes the outdoor air is at a much different, temperature, much different condition. For example, we'll talk in a later subtopic about how humidity and heat interact, to create a challenging situation to manage. But if it's 95 degrees outside and I want the temperature inside my office building to not be 95 degrees, I have to think about the energy costs to condition that outside air and have it at the right temperature. So remove the humidity and potentially remove the humidity and reduce the temperature. So to some extent, I want to think, well, I want to minimize how much of that outdoor air I take in, because that's going to be the air that costs a lot of money to cool. And so you can save money if you use more recycled air or recirculated or return air. And so, in case you didn't know this is, if you drive a car that has a sophisticated system like this, that allows you to choose, either are we always taking in outdoor air, which that's going to keep you more oxygenated, I guess, although I don't think it matters too much with all of the holes that are, in our cars that are letting in air otherwise. But are we conditioning only outside air, only fresh air, or do we allow some recirculated air within the cockpit, of our car, which is going to save on energy costs? You don't have to reheat or recool air that's already closer to your desired temperature. Okay, so we have a little bit of a cost, problem here, but basically once you have enough oxygen in a space, it's probably okay to say that's enough oxygen. More oxygen is not necessarily going to help your workers. It's just going to end up costing you more, in terms of energy costs to condition the air. So that's the role of this big old thing. So this is, you see these on every public building, every building of a certain size probably has some way to handle the air handling unit, the AHU. And so this is the thing that is, doing the ratio of how much outdoor air to return air that is cheaper to condition, and how is that air conditioned. That might all be done, within the same unit. Okay, so again, yeah, that's just showing you. This is the picture here, but that's representing this device inside your office building, or really inside your domicile, your home, currently apartment or house. All right. Okay. So it becomes a question of, how do these air handling units work? If I was an engineer that's designing these or is maintaining them, what should I be looking for? And in particular, the percentages of the outdoor air that is taken in versus the recirculated return air, that has implications for big time cost, but also the question could be, am I getting enough outdoor air to make sure that we're getting fresh oxygen as necessary to the people inside? So we can do some estimates here. We can do some calculations using this table here. I'm sorry, this graph here on the right. So, in most air handling units, this would not be unexpected that they would have sophisticated air temperature probes throughout the system. But if I can sample the temperature of the air coming back from, inside my building, which was dealing with all the people and everything, absorbing heat or cooling off or whatever, and going back to the air handling unit, what is the temperature of that air? So I can sample it there with my meat thermometer, right? If I also know, I check the Weather Channel or I check my phone, I know the temperature of the air outside. By the way, these are in degrees Fahrenheit. That's how this graph works with those units. If you use Celsius, this graph won't work. So use degrees Fahrenheit. If we know our outdoor temperature, and then assuming we have, a thermostat inside, we have a way to detect this is how much, or this is the temperature of the air, inside. And so we'll call this the temperature of the mixed combination of the outdoor air plus the return air plus energy added to condition it, the heating and cooling aspect. So think of this as the output of the air handling unit. This is the temperature that ideally matches the thermostat. Okay. So got an example here. So here's our workplace, and let's say it's all controlled here. It's all sealed up, and we've got interior and exterior air, and we can measure all these things. So outside, it's Texas, let's say, so it's 95 degrees outside Fahrenheit. It's hot. Inside, we don't want it that hot, so we're cooling the air, and so the air handling unit must have some ability to condition the outside air, reduce the humidity and to cool it. But similarly, we could do the same thing if I had to heat the air, right? But in any case, it's 95 degrees outside. It's 70 degrees in here. So there's a lot of energy that's probably being consumed in cooling that air. And yep, so it's 70 degrees in this room. Note, this is the temperature of the air that comes out of this unit. So it is the combined outdoor air plus the return air, and then heated or cooled to get to 70 degrees, I guess cooled in this case. So probably there's going to be some reabsorption of heat in that environment because it's hotter outside. So it's, we're all about maintaining a certain level of cool in here. Human bodies give off heat, equipment gives off heat. So let's say the return air is at about 75 degrees. So we've got a combination of pretty hot air and kind of warmer than we want air coming in. But one of these two sources is a lot cheaper, a lot less expensive in terms of energy costs, to condition. All right, so we've got these three temperatures, however we're collecting those. What is the percentage of air coming from outside? If this is my temperature profile, what's the way that the air handling unit works best with this profile? So I take the difference between the return air and the mixed air, and that is 75 degrees minus 70 is 5. And so I am looking at the curve that has a 5 on it, right? So I'm looking at this curve. Then, and I've got the absolute value of these because in our case, the outside air is warmer than the return air. But the difference here is 20. You can do that, and so I'm looking at looking at 20 along my x-axis here. And if I find the intersection of this curve with that point on the axis, I can then trace it back here, and percent OA, roughly 25% outside air, is what I might expect to be naturally kind of circulating with this sort of a profile. So then the question becomes, is 25% of the air moving through my building, which is measurable? Usually these air handling units, you can fairly precisely measure the amount of air moved per unit time in terms of the volume of the air. So if 25% of that volume is outside oxygenated air versus at least a lower oxygen content of return air, the question is, are we getting enough? Okay, are we getting enough to the humans inside, to support the level of activity that we're expecting? Well, there are answers to this. There are standards. And so ASHRAE, which is the American Society of Heating, Refrigerating, and Air Conditioning Engineers, has a standard. It's here's how much fresh outside air must come in, or at least the amount of oxygen that's required based on the activities inside. And so for most non-athletic indoor spaces, office spaces, conference rooms, areas where people aren't, running around too much, they're, in office attire, let's say, then this is the standard. So they want 5 cubic feet, that's a volume of air per minute, of outside air per person. So if you have a workplace with 100 employees in it, you say, well, I need at least 500 cubic feet per minute of air to be moved, to be, of outside air, to be added to my building at any given time. And additionally, we have to ventilate anything from outside air, anything that might be, emitting heat or absorbing heat, I suppose, but pretty much for the most part, you're ventilating things because they're getting hot and you're trying to, to give them a chance to cool off. So yes, any, high-tech, high-end computing equipment is very likely to generate heat, need some ventilation. So we add a little bit more outside air requirement here. So we need an additional 0.06 cubic feet per minute for every square foot of ground space occupied by non-human equipment that should be ventilated, like servers, like computer racks. For schools, we double all of that. Okay, so for regular adult office places, there's a certain oxygenation outdoor air standard. For children and in schools, at least according to the ASHRAE standard, we need 10 cubic feet per minute. It's a learning environment. We want to support, healthy children learning activities. And then we're also adding, so we're just doubling the non-human estimate as well. So 0.012 cubic feet per minute per foot squared of non-human equipment. All right, that's it for 15.2. Thank you.